The name of this video is Infinite Charged Plane. So, let us consider to have an infinite plane of charge. This is our plane. It's going to be indefinitely long in all directions. So let's sketch it here. And this again stretches all the way to infinite. So these dashed lines, that's what they mean. So let us call this plane capital sigma. As always, is a surface, so we call it capital sigma. And let's hypothesize that the charge distribution, which is a surface charge distribution in this case, continuous, is uniform. That is, the surface charge density sigma is constant. And again, this is an infinite structure, so it is better to deal with densities, sigma, rather than the total charge, which in this case would be infinitely large. We want to find the electrostatic field due to the entire plane anywhere in space. And for this purpose, let us pick, for example, an observation point here, capital P, where we place our test charge of +1 Coulomb Q naught right there. We want to find the electrostatic field at this point, which again represents any point in space. How do we proceed? As always, we need to follow the 4 steps of any problem in physics. So the first step is to identify, to choose a suitable coordinate system. In this case, we choose, obviously, a Cartesian coordinate system, because this is a plane, so it resembles very well a Cartesian coordinate system. It calls for it. So this will be the center, the origin of such a coordinate system. This is the z-axis. I choose to call it z. And here, of course, the coordinate system continues, the other side of the plane. This one, parallel to this, I will call it the y-axis, sorry, the x-axis. Let's call this x. It has to be right-hand rule. So if this is x, this is going to be y, and this is z. So this has to be x, following the right-hand rule. And so here, this is going to be our y-axis, and this is the origin of this coordinate system. So we have chosen a Cartesian coordinate system 1, origin x, y, z. The second step is to sketch the electrostatic field's components, the vectors associated with this charge distribution. So in this case, we can proceed in many different ways, at least in a couple of different ways, maybe even 3. So one would be to use an infinitesimal square here with dimensions dx, dy as our infinitesimal charge element, and then use Coulomb's law superposition principle to find E at this point P. Alternatively, we could even consider this as a disk with infinite radius. So we can consider this as a disk of infinite radius, okay? Where the origin of the disk is in the center, and so it's a very large disk. We didn't solve the problem of the disk yet, so I will not choose to follow that path, but we could, and we would obtain the same result. The method I like to use in this case is to use the knowledge we already acquired about an infinite straight line, and so to draw here a stripe infinitely long along the x-axis. The width of this stripe, which is located at location y, So this point is a positive y. The width is dy. So it's infinitesimally small, but infinitely long. Similarly, on the other side down here, at location minus y, we can have another stripe, a similar stripe like this, also infinitely long, with the same width dy. Now, as in the case of an infinite straight line, this is an infinite plane, we have an infinite set of such pairs at location y minus y with dy. Okay, so that's why I choose only one of these infinite pairs, as always. So this fact of using infinite pairs again is because there is a symmetry, and again we will discuss about symmetries later on in another video. So now let's focus, for example, on this stripe here. So we know that the field of an infinite line, which is what it is, it's lambda divided by 2 pi epsilon naught in the radial direction, times r, where r is the distance between the line and this observation point. So we know that the electrostatic field due to this line goes in this direction, and it looks like this. Note that this line is infinitesimally small, even though it's infinitely long. So the lambda, which we have in the numerator of the electrostatic field of an infinite line, in this case is going to be a d lambda. And how do we find the lambda? We know sigma. Sigma is Coulomb over meter squared. So we need to multiply this times dy. So sigma times dy is our d lambda, and I call it d because it's infinitesimally small. Okay, so sigma dy, which resembles the lambda we had in the field of an infinite line, which again, I remind you, it looks like this. R is a distance, let's just call it d for now. And this is the absolute value. The direction is radial in that case. Okay, so we know this d lambda. So this will be a field dE. In particular, this is the field dE vector due to the stripe at location y. Similarly, from here, I will have a field dE vector due to the stripe to the line at minus y. And so we have infinite pairs like that. So if we look now, so this is our field. If now we want to find the degrees of freedom, step 3, we proceed as always. So we look a little bit more closely at these two fields for one pair, and we notice that while the z component sum up 2 times, in this case, for this pair, the y components cancel out, as always. So we expect only to have a z component. So the degree of freedom of this system is z. That's where the particle, you know that I place a capital P here, at point capital P, can accelerate only along the z-axis. All right. So now the hardest part of the problem, in my opinion, is done. This is what really the problem is all about, the understanding these basic qualitative concepts, and then the quantitative analysis is what we're about to do. It should be straightforward from this. Let's define a few quantities here. So if this angle, I call it theta, which is the same as this angle, for example. Let's call this distance, which is d, let's call it just d. So d is the distance from this point to this point, this distance here, okay? So this is d, okay, like here. So we know that d from the Pythagorean theorem is the square root of y squared plus z squared under square root. We also know that y divided by z is the tangent of theta. We're about to use that in a minute. I will write on this side of the board. Okay, so the next step is step 4, where we qualitatively solve the problem by means of Coulomb's law, plus the superposition principle. The superp means superposition principle in this case. We want to use Coulomb's law and the superposition principle, as always, which in this case is an integration. So how do we proceed? We already know the result for one of these lines. This is an infinitesimal field, dE. Okay, dE is going to be given by lambda, which in this case is d lambda, so sigma dy in the numerator. In the denominator, we have 2 pi epsilon naught times d, which is this quantity here, under square root. And again, in the numerator, we have lambda, which is a d lambda in our case, so sigma dy. So we are integrating along y. So this is the infinitesimal field, but note that only one component, which is the one projected along z, counts, and this is the cosine of theta. So we need to do times cosine of theta, and this is the only contributing component, which is the uz component. The degree of freedom is only z. Okay, so now we need to integrate. In order to find the total electrostatic field E at this observation point, at this test point, we need to use the superposition principle. So note that we can integrate either from minus to plus infinite or from 0 to infinite. So let's integrate with y for simplicity, from 0 to plus infinite. So since I'm only doing half of it, I need to do at times 2. I need to remember to do that, and I'm about to do that. So sigma is a constant of integration, so we can keep it outside. In the denominator, we have 2 pi, or constants. Epsilon naught is a constant. And uz is the direction. Here we have sigma. Then we do the integral. Instead of from minus to plus infinite, from 0 to plus infinite is the same thing. So if I do from 0 to plus infinite, I need to multiply times 2, and this 2 goes away. These 2 2's go away. And in the integrand, we are left with dy divided by the square root of y squared plus z squared times the cosine of theta, which we can keep as such. You don't have to rewrite it, and uz we already put it there. So let's remember that y divided by z is the tangent of theta. So y is equal to z times the tangent of theta, which also implies that dy, we have done exactly the same trigonometric substitution in a previous integral for the infinite straight line. So dy is z divided by the cosine square of theta, d theta. Now we use this substitution into our integral. And it's the same kind of integral we have seen in a previous video for the infinite straight line. So the electrostatic field E eventually is given by sigma over pi epsilon naught uz. Okay, now we are integrating. Since we switch from y to theta, theta goes in this direction. So for y equals 0, we are down here. So the angle is 0. So we want to do the integral from 0 to eventually, when we go to plus infinite, the angle is going to be a full pi half. From 0 to pi half, plus pi half, plus infinite. dy becomes z over cosine square of theta, d theta. We substitute this dy here. We have another cosine theta here, not to forget it. So let's put it right away. And then we have this denominator, which is similar again to an integral we've done before. There we had the power of 3 half. Here we have the power of 1 half. So if I substitute y in here, I obtain d squared tangent square theta plus d squared. So d squared I can factor it out and square root it. So we obtain in the denominator 1 over z, because it's under square root. And then we're left with the square root of 1 plus tangent square theta under square root. Okay, so I remind you that, so this z and z go away. This is nothing but 1 plus sine square over cosine square. So it's cosine square in the denominator, sine square plus cosine square, which is 1. So it's 1 over cosine square under square root. So let me rewrite it. So this is 1 over 1 divided by cosine square theta under square root so it's 1 over 1 over cosine, so it's cosine. So it's a cosine which multiplies this cosine, gives a cosine square. So this quantity cancels with this cosine square. And we are left only with the integral in d theta, which gives us pi half. And so to conclude here, we find that the electrostatic field E is given by sigma divided by, so pi goes away because it's pi half. So it's sigma over 2 times epsilon naught uz. Okay, and this is a very important result. This is a very important result and it's worth circle it here in yellow. Okay, so the result is sigma divided by 2 epsilon naught uz. Okay, so let us try to plot this field here. And so, for example, if this one is our axis with the magnitude of E for an infinite plane of charge, this is our z-axis, this is the origin, okay? So in this case, the electrostatic field on the positive side, which is for z larger than 0, we have a plus because the field points in the z direction. So we arrive at this point here. And this quantity is sigma over 2 epsilon naught along with z. On the other side, obviously, the field is mirrored, so it points in the negative direction of z, so it's the same magnitude, but with the negative sign, minus sigma over 2 epsilon naught. And so it looks like this. And note that in this region, we have a discontinuity of the first kind, the amplitude of which is sigma over 2 epsilon naught minus minus, which is plus sigma over 2 epsilon naught, is 2 times sigma over 2 epsilon naught. And so the discontinuity, which is this minus this quantity, is sigma divided by epsilon naught. Note that this is a very important result. Why is it a very important result? Because as it turns out, when we will study case 2 for the boundary conditions for, well, it's case 2 of Maxwell's equations in electrostatics. So case 2 of Maxwell's equations in electrostatics, we will find out that for a surface charge density like this one, there is a discontinuity of the electric field going from left to right compared to this surface, which is exactly sigma over epsilon naught. So this example confirms a theory, which is case 2 of Maxwell's equation in electrostatics, confirms it for an example, for a particular example. Additionally, as a last remark here, note that finding the electrostatic field of an infinite plane of charge is the first step towards the capability to find the capacitance of a parallel plate capacitor. So, after a few videos, we're already in a position to be able to almost find the field, the electrostatic field of a parallel plate capacitor. And in fact, I let you think, so imagine that after a few lectures, we can already do the first part, basically, of the radio, of the tuner of the radio I've shown you in a previous video. So I think that's quite exciting. With just a few tools, we're already there. So we're already at that stage. This is extremely exciting, in my opinion. So I let you think in Piazza. Think about the following problem. What if I give you a double plane of charge? So I have one plane, infinite, again, like this one here, and in front of it, I give another plane as some distance, whatever you want to call it, let's call it capital A, between them. What is the electrostatic field for this distribution? Please think about that in Piazza. Alright, so in this video, we have done the very important problem of the infinite charge plane. We have seen that it can only be along the z direction and is constant, it does not depend on z. The Cartesian coordinate system is what the system of choice in this case. The trigonometric substitution to solve the integral is similar to that for the line of charge, but we have a power of 1/2 instead of 3/2. Okay? And here we plot the field on the left and on the right hand side of this plane. And the reason why on the left is negative is because obviously we need to mirror it. So if here it goes in this direction, here it goes in that, which is opposite of z. The discontinuity sigma over epsilon naught. We will confirm this theoretically in case 2 of Maxwell's equation for electrostatic soon. This is the first steps towards finding the capacitance of a parallel plate capacitor. And I ask you, in fact, to find the electrostatic field of 2 planar charges facing each other, which is nothing but an approximation of a parallel plate capacitor. Thank you.